Well, now we describe and define Ampere's law. This will be an important discussion because it is one of the four results that Maxwell used to fully describe the phenomena known as electromagnetic radiation. Really important stuff. Yeah. So some preliminary thoughts is that Gauss's law that we've grown to know and love relates electric fields and charge distributions. Remember, we had electric flux is closed integral of E dot dA, which is Q enclosed over epsilon 0. Rolls off the tongue. Now, Ampere's law, as we study magnetism, does not relate magnetic fields and current distributions in an analogous way because the magnetic flux, being the closed integral of B dot dA, since you don't have any magnetic monopoles, the flux, any flux into a surface also goes out. So we saw that that's zero. So Gauss's law for magnetism cannot be utilized to say, let's describe what the magnetic field is. This formula won't do it for us because it's zero. What we have to do instead is take a line integral around a closed path that encircles current. So let's take a look at what that means. We'll have the closed integral of B dot dl. Not B dot dA, but B dot dl. So here's a current coming out of the page. And we've already described the size of the magnetic field from that. It's at radius r. So here is the B field. Thumb out of the screen, fingers encircle the direction of the magnetic field. And it's also going to be the direction of our integration path. So there's our dl going around this current, actually going around in the direction in space of the magnetic field. Notice that they're in the same direction. And the B itself is mu 0 I over 2 pi r. Let me pause for a moment because we just learned about the magnetic field produced from a current loop. This is not a current loop. This is a line of current and the associated circular geometry magnetic field resulting from that line of current. If this was a current loop instead, then we found that in the center the magnetic field was mu 0 I over 2a or 2r. So the formula for that situation, different from this, is mu 0 I over 2r, not 2 pi r. Very similar, very easy to conceptually convolute in our minds. So be warned. Now, B and dl are in the same direction, and B is constant magnitude because the radius is the same everywhere. Okay. So the closed integral of B dot dl, B constant integral of dl. So that's mu 0 I over 2 pi r. There's B. An integral of dl, that's obvious. That's just the circumference, which is 2 pi r. Oh, wonderful. That whole thing is just mu 0 I. And so we have the closed integral of B dot dl is mu 0 I. And notice that you don't see radius in here. That makes sense because B is inversely proportional to r, but the integral of dl is proportional to r. Therefore, those two effects cancel. So here's almost the result that we're looking for. And now let's continue on with this idea. Well, I hope all of you have your right hand attached because we keep seeming to have right hand rules that we can utilize that wonderful hand. If you only have a left hand, I apologize to you, but you can use your left hand and just reverse everything. So anyway, here's our little right hand rule. Curl the right hand around the integration path. And if you do that, the thumb will point toward positive current. Let me show you what I mean. So here's a current and circular region around there. Here's our integration path. It's clockwise. So grab that line of current with your grubby right hand, thumb pointing into the screen, fingers circulating in the direction of dl. Well, your thumb points into the screen, right? So the positive current must be in. So the actual current, which is out, is therefore defined as negative. Simple as that. So if they're in the same direction, positive. Opposite directions, negative. All right. Now let's do an example where we actually integrate around an entire closed path. And let's see the result we get. So here's our path. We have A, B, C, D, those locations. And our integration path is going to be counterclockwise. So there's DL along there. We put the DLs in the proper direction so we can visually see what's going on. So that's our integration path. Now we also need to put the B field along these paths. And one example for each will suffice. Because you know a current coming out, thumb out of the screen, fingers circulating in the direction. Here at the first segment is our B field, perpendicular to DA. Along this path, we see the B field is in the direction of the integration path. Here is perpendicular again, and finally, anti-parallel. All right. Now, we have radius 1 for B1, and we have radius 2 for B2. Let's consider then, as we integrate along this path, we have this angle theta, which is actually pi over 2. So let's evaluate the entire integral around the path. We have to piecemeal it. Closed integral of B dot dl is the same thing as the closed integral of the parallel, the B that's parallel with dl. So let's start at A and go all the way around counterclockwise. So we have B1, constant value, integral from A to B dl, plus 0, because there is no parallel component of B with dl, from B to C, plus negative B2, integral C to D of dl, because the B field and dl are oppositely directed, and then 0 again, because they're perpendicular. So we only have two pieces here. So the first part, mu 0 I over 2 pi r1, but dl is r1 theta, so the r1s go away. That's kind of nice. Then we have the other one, mu 0 I over 2 pi r2 theta, because that's the integral of dl, but the r2s go away. All right, so we have the whole thing being 0. So notice that if no current passes through the area bounded by the integration path, if there is no current in there, the line integral will always evaluate to 0. The only time you're going to have a non-zero evaluation of that integral is if you have some net current enclosed by the integration path. Voila. You know, it's always important for the specific case we look at, which we just did with a nice symmetrical quarter circle, make sure it works in the general case, that our theory is applicable there as well. So now we have a generalized integration path. So here it is. We got a single current in the corner there, radius r, and a little differential angle d theta. And so we have our little dl along that d theta. And the B is in this direction, just with the right-hand rule. All right, so perpendicular to R. And we have phi, the angle between the B field and the dl, which is going to give us, relate to the component of the B field that's applicable here. And so the part that is of the dl that's in the direction of B is just r d theta, in the same direction as B. So B dot dl is B dl cosine of phi, and that gives us B r d theta. All right. Then the closed integral of B dot dl equals closed integral of mu 0 I over 2 pi r. Now B is varying. We can't bring this out because r is varying as we go around this path. But it's always this value of r times that r times d theta. So those r's go away. We have mu 0 I over 2 pi integral of d theta. And of course d theta is simply the angle going all the way around that path, which is simply 2 pi. This is wonderful. It gives us the result that we had earlier. Closed integral of B dot dl is mu 0 I. So there it is. Now, Let's check out current being outside of the path of integration. What do we get then? All right, so here's how I'm going to do it. Check out the path as we integrate around this whole thing. We notice that where we started is where we end, and basically when we're up like that and back down, there was no net value for the integral of d theta. It's 0. We didn't go around the thing. We didn't start and end at two different positions. We started and ended at the same position. So 0. Now, if multiple conductors are enclosed, then the total B field is the contributions from each one. And closed integral of B dot dl will then be the mu 0 I, but I is the contribution from all the currents. And each one of them currents could be going out, going in, oppositely directed, same directions. We have to use the sign rule. So if circulating our fingers around in the integration path, our thumb points to positive current. Some of these might be positive, some might be negative. Just algebraically add them. And then we have our final result for Ampere's law. And there it is. Closed integral of B dot dl is mu 0 I enclosed. So the only thing changed is we just added this enclosed. How much current is enclosed by the path? And we have our final result. Just a couple of pertinent comments pertaining to our Ampere's law development. If we consider closed integral of E dot dl as we go around the integration path, it's 0. Why? Because the electric field is a conservative force field. And there's no net work that electric field does when you do a complete path from point A, any place, to point A again. And the force is QE, a conservative force. Well, shouldn't closed integral of B dot dl be 0 also? In other words, the question is magnetic field, like electric field, a conservative force field? Keeping in mind the magnetic force is QV cross B. Now that's everywhere perpendicular to the magnetic field. Since it's perpendicular, the integral isn't related to work. Doesn't do any work on a charge. The closed integral of B dot dl is only related to the current bounded by the path. So the magnetic force is not a conservative force. It depends on the speed, not just the position of the body, as in the electric force. Well, so there you go. Now, we derived Ampere's law using a long straight conductor. That's how we arrived there. Let's reverse the order and use that law to derive the B field of a long straight conductor. So here's our conductor, current coming out of the page, and here's the radius. We're going to find the B field at radius r. Now, there's the direction of B field. Now, closed integral of B dot dl is closed integral of B parallel to dl. So that's B, constant size, times integral of dl 2 pi r. And that's mu 0 I enclosed. So that's our formula. So let's solve for B. And there it is. Mu 0 I over 2 pi r. That was easy. That's awesome. Thank you very much, Mr. Ampere.